So, back to gradient-based learning. So basically, right now you should have like a high-level overview of what machine learning is if you haven't started coming into these workshops with any prior knowledge. So, goals over this workshop is basically we're going to introduce the idea of what like statistical learning is. So if you don't know like what learning is in the context of like computer science or math, like how do you have like an equation that like learns, what does that actually mean? So basically, and then from that we go into like cost and error functions. So how do you like quantify how good or how bad a model is? And then we go into gradient descent. So basically, like how do you optimize these error functions? How do you decrease the error of the model so that you have something that actually learns? And then we go into like variations of gradient descent. Gradient descent is like the most popular optimization algorithm, but there are different like tricks that you can do that will improve this. So let's start by introducing the learning problem. So let's say you have like some data D. This could be like anything from like a massive image data set to something as simple as basically just some linear data. And you might have like seen this like data like this if you were just like a chem lab or something plotting data, and then you click like line of best fit on Excel. That's basically machine learning, and we're going to learn actually like how to do that. So you start with some data. And then you need to make an assumption about this data. You need to create a model based on this data. So we observe that this data is like linear. It just follows that general trend. So how do you like model linear data? With just like the equation of a line, basically. We've all seen this. So it's just like y equals mx plus b. But in statistical learning, you break this down into what's called like parameters. So that would be denoted by theta 0 and theta 1 there. Theta 0 corresponding to that y-intercept, and theta 1 corresponding to that slope. So that's basically just moving that line around. And you want to find values for these parameters such that it's going to model this data effectively. So let's come down, what is learning then? So it's like the approximation of some unknown function f based on some data d. So there's this ideal function out there that generated this data like in nature. But nature is like, you're not really going to be able to express that really well. So we approximate it, and that's why you have that f hat there. It's the approximation of this ideal function, that function that is mapping this input to that output. So we also want to take some input, and we want to give an output that's very similar to something that you would see. And that's where you get that predictive power out of these statistical models. But how do we set these parameters? You want these values that are going to accurately predict this data. So the question becomes, how do we set these parameters? So we use gradients. But what are gradients? I'm not going to assume that you've had like a lot of math background. Basically, if you haven't even seen calculus or just been Calc 1 or something, you should be able to follow along here. And I'll explain. Feel free to ask questions at any time. So basically, gradients are a general case of a derivative. So a univariate function, just like x squared, has a derivative of 2x. So at any point on that function, it's just like that tangent line. It's that slope. It's that instantaneous change at a certain point. So the information it's giving you basically is that that function is changing at this rate at this instant. Now we want to generalize this to multivariate functions because when you have these models, you're not going to just have like one input or like one parameter. You're going to have all these very complex functions. So you need the general case, and that's the gradient. Basically, if the gradient is like in the form of a vector, but if you haven't like aren't familiar with vector, just think of it as a list of values. But within this list, the values are going to be just like these derivatives with respect to each of these inputs. So in that function right there, theta 0, x 0, and so forth, theta is the parameter, x's are like these inputs or these features from the data itself. So basically, and that is like a really small example right there with just two variables. The derivative of that function with respect to x0, that's just going to give you 4. So it's like when you like tweak that input by a little bit, it's going to be changing by about that much. So this is the information you're getting from a gradient. So right here is basically what I want you to take away from this. The gradient tells us how much the output is going to change, of some function will change with respect to the parameter of that function. So this is the information that you need, and that's going to help us learn down the road here. So make sure this is the overarching thing. Don't worry about like doing the exact math. You can sit down and play with that yourself, but this is the idea that I want you to take away from this. So how exactly is this information used to learn? We have this idea, again, that the gradient tells us how much the output of a function will change with respect to a parameter of that function. So we have that. Now we use cost functions. We need a way to determine, okay, like going back to here, let's say we just start with like a random guess. This line isn't nice there, it's not pretty. It's something, just a random guess, so you have a random y-intercept and a random slope, and that's just like not describing the data whatsoever. So you need a way to measure how good or how bad this model is, and that's where cost functions come in. Basically, it's going to measure the error distance between a hypothesis of this model and the actual ground truth of the label correct answer that the data set provides you with. So, like, let's say right now we had like just black box model. You don't know what's in it. It's outputting these three values, 0.1, 0.2, 0.3. But you know, because you have a data set, that the correct answers for these inputs should have been 0.5, 0.8, or 0.2. So what you do is you just take the difference between these values, and that's your error distance. And basically that last part right there, the least square error, is a cost function. Basically it has these extra operations in it, kind of like the squared values of these differences and then 1/2, just to make the math on the road a little easier. So basically that key idea, takeaway from here, is that you're measuring the error distance. Okay. So there are different cost functions, right? And you probably like blog posts or like tutorials, papers, you're going to see this referred to like all these different names. So you have cost criterion, objective, loss function. They're basically all referring to the same idea that you're measuring the error, you're measuring that distance. That's going to give you a quantitative explanation of how good or how bad this model is. So the cost functions are going to be tailored per the model. So down here we have two examples. You have a regression example, which means it's like that line. There's going to be a continuous value for every input. The classification, you're trying to decide, hey, is this a dog, is this a cat? So you have like two different bins, right? So you're trying to predict, okay, like it's in this one or it's in this one. It's not like, okay, what's the value at this point on this like function, right? So you need different cost functions to be able to account for this and to be able to quantitatively explain, again, how good or how bad a model is. So let's take a case study of least squares error cost function, okay? So what you're doing is you have your hypothesis. That's denoted by h theta, xi just being a single training example, training input rather, and then yi being like the correct answer for that input, what you would expect. And so that hypothesis represents pretty much your model right there. That's your prediction that comes out of your model. So again, you're taking that distance between that output, and then you have a value right there, and then you square it to make sure it's like not negative, so you can compare better. And then you have 1/2 because that's going to make the calculus down the road easier when we need the gradients, right? It's the derivative. So a good way to like see this is right here. If you have that line right there, right now it's all nice and pretty, but it's like literally that distance between each of these data points and this line that you're trying to predict. So you can actually visualize this as a distance. And so you're trying to minimize that not for just one, but for all of these. So that's why you're summing across all of these. And so in total, you're trying to minimize all those error distances. So now you have the cost function. You have a way of saying how good or how bad a model is, right? So you want to be able to decrease that error. You can say, okay, this is the cost, this is like the loss that's happening right now in this model. You want to decrease that. So it's framed as an optimization problem now. So the derivative is going to give you the change in this cost function with respect to some parameter. So you want to find the changes in these parameters so that this cost function is going to come, the output of that cost function is going to come down. It's going to be less. You're minimizing the cost. So consider this like simple cost function example. So like x squared derivative 2x. Right? If you've like taken calculus before, you've probably done problems like this. So like, okay, when is the setup minimum, right? You just set that equal to 0, and then it's nice and easy, and boom, you have your answer. That's the value that you want so that this function is minimized. But you can't just do that when you have these like neural networks with like billions of parameters, and then it's really large like loss space. It's not just gonna be a nice, easy like parabola. So you need a way to like find this without just trying to do the calculus for it. So what we use is called gradient descent. Now, gradient descent does come with some assumptions. So the assumption is known as the IID assumption. That means that each of these data points in these data set are independent of each other, meaning that one isn't going to influence the other, or changes to one isn't going to have a change to another, and then identically distributed. That means that they're kind of coming from the same thing that's generating them. Like think back to that ideal function back there that's in nature. Like something is coming out and it's creating this. So these need to come from like the same distribution. Otherwise, how can you really like learn something that's all over the place? So that's an assumption the gradient descent is based on. Now we wouldn't use the gradient here to like iteratively traverse the parameter landscape. So instead of having a one and easy done, like that set it equals 0, and so then solve, you have to like iteratively make these changes. You'll be like, okay, this seems like the right direction to go, so let's take that. And so we'll get into that. So it's important to note right now that the gradient is the direction of the steep descent at that point. So we're going to do gradient descent. Now let's break down this equation. So these are your parameters, right? Theta j. This is like one parameter. And then right here, that's your gradient. So that's going to give you that direction of steepest ascent. But we want to go down. We want to find that minimum. So we subtract from that value before. So think about on this curve right here. These are all your parameters, right? So over here, these are the parameters that are going to give you that loss. Now that loss is pretty high. We want to be here. So we want to take that gradient, okay? And that gradient right there, that's going to be like just positive value, up and to the right. So that's going to give us a positive gradient, but we're subtracting. So that's going to take us to the left there, and then you can see that we're slowly stepping towards that minimum. And since the gradient mostly just gives us the direction, right? It's not telling us how far to like step. So if you think of gradient descent as like you're a hiker on a hill, but you're blind. You can't see like very far in front of you. You can't just see and be like, oh, I just need to walk there. You can only just stand there and you're blind. You just kind of like feel around. You're like, okay, how steep are the areas around me? Because if you just take the steepest path, you're going to get to presumably like the lowest point. But you don't know how far of a step to take. You don't know if you want to jump down or if you want to take tiny baby steps down. So you use the learning rate, which is alpha right there. So that basically just tells you how big of a step do I want to take. And then you just update the parameters based on that information. So now we have the learning rate. This is like the main hyperparameter. So a hyperparameter is different from these other theta parameters because it's not being learned. You're just setting it. Now that method is kind of arbitrary, but there are methods that you can go into that will like learn how to like set this well, and we'll actually touch on a couple of those. But for now, if you were just playing around with something, like ideal learning rate values to try would just be something like 0.1 and then go like a magnitude lower each time and just see which one does better. So the issue you're going to get if you have a learning rate that's too big is you're basically going to step over this minima. You might miss it. And then you might, in that animation down there, you might step over and then it's like, oh no, I need to go back, but it's too big again, so you just keep missing and you're just going back and forth, and that's just not going to work well. But, so on the other hand, you might think, okay, let's just have a really small value, okay? Like, if I just inch my way down, I'm definitely going to hit it. And you'd be right, but when you're dealing with these data sets that like have 100 million images or parameters that are just, they're just tons of these parameters, it's very computationally expensive to make that many small little updates. So you want to find a nice balance between like the size, between like the problem that you might miss it and the problem that's just going to be too expensive. So it's a bit of trial and error here. Another problem is the idea of like these settle points. So the gradient right there where all these balls are like falling to, that would be 0 as well. So to them it looks like a local minimum. But we can clearly see that that's not. And so these are like problems that are going to exist not just in like three-dimensional space, but they're going to be like higher as you go into like even like 100 million billion parameter space. These are all problems that you're going to encounter. So you need to think about how are we going to like beat these problems. So like a simple one, you just add some kind of random noise, right? Like you go down there, but you're not taking the exact step that the data is telling you exactly to take every time. So there's kind of like this kind of randomness in there. So you might find a place like, oh, now I can see that there's a place to go over there that you couldn't see previously before. So there are different types of gradient descent. What we've been describing so far, just that simple update, is batch or vanilla gradient descent. Basically, the main difference in this one is that you're taking into account that entire data set. You know, like which is the best path to take because you're like averaging the gradients of all these data points. And then there's stochastic gradient descent, and that's just using one of the images from the data set instead of all of them. And then there's a third variety called mini-batch gradient descent, and that kind of takes the best of both worlds. It puts them together, and it's going to balance that computational expensiveness of having to calculate this gradient over the entire data set versus just one value. And we also saw before on this slide that having a little bit of random noise, indicated by like stochasticity, also known as like just randomness, that it's going to help you out, and it works very well. And then you also have Adigrad and Atom, which are two, they're called like adaptive learning rate methods. So we talked about all these issues with the learning rate. So wouldn't it be nice to be able to like not have to like set this hyperparameter? And these two methods are attempts at doing that, and we found that Atom actually works really well, and Atom actually turns out to be one of the most recommended ways of optimizing your cost functions. So batch vanilla gradient design. So this, think of the batch size just like a batch, like you have a batch of cookies, right? It's just a batch of the entire data set, right? So this loop here is how many times you want to go over this data set on the other side. And that's known as an epoch, or an epoch. Depends on who you ask. But basically, this gradient right here is a summation. It's pretty much think of it as the average of all the gradients calculated from every single data point, every single like label. And then you have your, this is like, we already talked about this. And what this is going to give you is going to be proper steps taken every time you take a step. And so it's going to give you a nice, easy step and direction to converge to that local minima. And then there's stochastic gradient descent. So the difference between batch gradient descent and stochastic gradient descent is essentially that you're only using one data point at a time to calculate that gradient. So it's going to take you many iterations to go over the data set, but you're taking a step every time you just use one data point. So while one data point might lead you in a different direction than the average of the entire data set, it's still eventually going to take you to the right location that you want if you do it a large number of times. So again, each time the full data set is an epoch. So this is going to make for a noisy descent, as you can see right there. Like one data point right here is going to take you in a different direction than if you average the entire data set. And so you're just taking these random like steps basically, but eventually it's going to take you in the same location that batch gradient descent does. It might be worth noting that you might end up bouncing around that minima that you're looking for, but it's good enough to say that that's where you want. So this is what like the update rule is going to look like. We have this outer loop here through the entire data set. Now, for every time you're going through that set and you're updating by just one, so you're going to have to go through the entire data set and then make this update as well. And so this image right here would be the loss on the y-axis and then the number of iterations through the data set. So you can see that's going to be like a noisy up and down. It's not taking you exactly where you want to go, but the general trend is exactly where you do want to go. So now we have mini batch gradient descent. So if you come back to here, the batch on this size is the entire data set. The batch size here is just one data point. Now, kind of taking the best of both worlds here and saying, okay, so batch vanilla gradient descent, that's going to be like too computationally expensive. We don't want to have to go through the entire data set. So stochastic gradient descent might be too noisy. We don't want to have to deal with all this randomness. So combine them. So instead of going through just one data point or the entire data set, you break it up into batches. Let's say like you break it up into you average every 32 data points instead. And so this right here, instead of this being the entire data set, this average of the gradient becomes the average over that mini batch. And so it's the same update rule, just how exactly you're calculating that gradient that you're making these changes based on is what changes. So those are really like the three main versions of gradient descent. If you have a good understanding of that, that will really help you out. And we actually are going to have a Jupyter notebook that we can go through that will have those, and you'll be able to play around with the differences of that. So I'll introduce that at the end of this. But right now, there are other tricks to help. If you remember back to stochastic gradient descent, right here, you have all these like noisy steps. It's not exactly going in the right direction every time. So what momentum does is it introduces this like short-term memory. through like this velocity term that's calculated up there. Now note that this update right here is pretty much the same thing as the same updates you've been seeing through all of these, except you have this value that's being added to that gradient instead. And that is basically just a gradient from like the previous time step. So it's adding that momentum behind it. It's saying, okay, we took this step before, let's take a step, we're probably going to take a step in that same direction again, so why not let's push through that, let's just reduce all this like scattering and just go right to where we kind of want to go. And it ends up really helping. It reduces this oscillation and it puts you in that direction towards that minima that you want to be at. And so in practical tip here, it's like the momentum term is usually set to 0.9. And what 0.9 does is it makes sure that it's not just infinitely adding and adding. So it brings it down and you're just adding a fraction and then taking the fraction of that and so forth, such that you're not just getting these enormous values and then just taking these massive steps. So now we have addigrad. Addigrad doesn't really do anything with momentum, but keep momentum in mind for later. Addigrad, going back to this problem that we had with the learning rate, we want to be able to like set this learning rate in a more principled way. We don't just want to like guess and check if this learning rate is going to do well. So what addigrad does is it makes sure that there are large updates for infrequent features. So features are, just think of them as the inputs. So if you have all these inputs, and you see these things like recurring, the same patterns and the same inputs, they're indicating this thing, and they want to change the overall function by changing these parameters. So, but there are also these other infrequent features that also are going to give some important information on which way to go to find that minima. So what this does basically is it's going to keep track of all like the changes that it wanted to make. And if there were these large changes that it kept wanting to make, it's going to keep some of that, and then it's going to divide by that. So it's going to decrease that learning rate. And that's what's happening right there with that g, and then that alpha being that learning rate from before being divided by that. So it's kind of decreasing that learning rate for these features that have always been showing up and really trying to take this over. Meanwhile, these infrequent features, they have something valuable to say too, and they're going to get you to that better minima. So they aren't going to have as large a thing. So alpha isn't going to be as small. But this relies on accumulating that information throughout training. So you're going to have to be adding continually these gradients squared, and you're just going to end up with this like massive g value by the end of this. And basically you're going to be dividing alpha by a massive value, which is just essentially going to bring that value down to effectively 0. So that's a problem. Now, addigrad itself isn't something that's very popular. I have this in here because it's the next step to atom, which kind of combines momentum and addigrad. So you have the ability to have these adaptive learning rates, not needing to set it and play around with it as much. And you have like the push that momentum gives you. So think about it this way. So if you see this update rule on the right, that's pretty similar to that square root with the g under there, just this time it has that p of t. And so if you go back to momentum, it's adding that previous gradient to it. And so a little different notation here, but these g of t's and g of t squared stand for the gradient, which is the same thing as that gradient symbol with the j cost function. So that m right there, think of it as like the momentum in this case. It's going to be that previous gradient plus like the new gradient. And so those betas in there get rid of that problem in addigrad, where you're just having this linearly scaling collection of all these like gradients, basically like how much these like frequent and infrequent features are like there. So it gets rid of that problem because these values are going to be set to like a fraction, just like that momentum term was set to like 0.9. So you're never going to have that massively increasing and increasing value. So you can see in this update rule that it's a combination really of addigrad and momentum. So all these courses now, like under carpet, these like CS231N, they actually recommend that Atom be like your default optimizer that you go to. Atom came out, I believe it was 2015, out of someone from OpenAI. Yeah, so basically this is something that's pretty new. So it's good to like keep up to date, and hopefully that will be helpful for you. Um, so basically that's kind of like the overview of gradient-based learning that you need to know right now before moving to like neural networks and stuff. And it's kind of like a cool, fun question to ask, like, is there anything else besides gradient-based learning? Instead of just using that information that you get from gradients, like how much one change in this parameter is going to change the output of that function, can you like optimize these cost functions without gradient-based learning? And you can. And one method is evolutionary models. Basically, think of it as like a guided random search. So you need like three things for evolution. You need variation, heritability, and selection. You need variation because in a population of whatever you're dealing with, whatever you're trying to optimize, they need to be different from each other so you can have a selective force that's going to be able to say, okay, this one's better than the other. Let's let that one like mate, have like offspring, and then more variability, and then eventually you might find something where it's like, okay, this is working really well. So then you just go cut off and you do it, and you're done basically. So that's pretty much it here. So we have this Jupyter notebook. Basically, we outlined like these three main methods of gradient descent. Atom and Adagrad, you could probably give an entire lecture for multiple like hours on like what exactly makes them like go. So we've implemented these. So it's these three: batch gradient descent, stochastic gradient descent, and then mini batch. So you can kind of see the differences in these losses that you're going to get from using these different variations of gradient descent. Yeah, so if you want to copy paste that link, it's there. Does anyone like have any questions? Something that's not clear? Yep. Yeah, yeah. For for Adagrad. So it's kind of like, so basically people say that this is going to work really well on sparse data. So that means like data where you're not really missing values, just that those values are pretty much zero. So think about like a sensor. It's going to be projecting, and then it's only ever going to record that change. So a ton of that data is going to be just like no change at all. And that's still valid data, but it's not really important much. You don't need to constantly make updates to the like overall function via these parameters just to say that nothing's going to happen. So it's kind of minimizing the effect of basically saying like there's no change, and then maximizing the effect saying that there is going to be a change. Because like on a sensor, change might only happen like who knows how long in a day, depending on like that sensor. Does that make sense?
How do we avoid like the global movement problem? For example, I know that gradient descent has a problem where it will get stuck at a local minimum as opposed to like the maximum of that function.
Yeah.
What current methods in this area?
Yeah. Like that's a very active research area, but it actually turns out that there are some of these local minima that actually do pretty good, like even compared to like the global minima that you would be like searching after. So it's not necessarily about finding like what exact global minima can you find. It's kind of just saying what is going to work well. You can get to like massive like theoretical analysis. Simple like, can you get into this? I can get you some papers if you'd like.
Also, I just want to add, like, one simple thing that Kevin mentioned is that you can try to add random noise to kind of jiggle you out of sharp global minima, which is kind of, you could say it's a stopgap, but it does give you better results. And I believe like ensemble models, if you train like a bunch of models together, kind of average the results, that tends to bring you closer to global minima. As opposed to, because like if you train a single weak model, it's not going to perform very well, but people find that if you train a bunch of these weak models together,
I think that sounds a bit but I think like what Devin was trying to say is that you can take local minima because essentially what you're doing, right, you're looking for the expected value. So as long as an expectation is fine, then that's why I'm taking local minima that performs well. And like other things that you can do while training, which I think someone else gets later on, are things like validating. So as you're training, you can say like when let's stop, or you should like increase your win rate and whatnot. And so these are other ways. But generally, local minima is not an issue.
Anyone else have any questions? Yeah, I'll give a brief overview of this Jupyter notebook here. So basically, it's going to start off like we have that like linear data in the beginning. It's like setting up like the learning problem. So you're going to have like some data. So basically, it's just taking a line. It's going to add like some random noise to it. So now we have like some nice, very clean linear data. And now we just make it like a guess. So it's like what's the random value for like the slope of the prediction? What's the random value for like the line intercept? So it's like you just kind of started, you're just kind of making a random guess, and now you need to optimize that. So just going through, you're going to use gradient descent to optimize it. And we're using that least squared error as a cost function that we saw earlier. And then it comes down, and then we start with mini batch gradient descent because you can kind of view stochastic and vanilla gradient descent as a special case of just like mini batch gradient descent because your batch size is like just 1 for stochastic gradient descent, and it's the full data set for like vanilla or just plain batch gradient descent. Yeah, so we could like play around with like number of methods to training for, learning rate. So these are like your hyperparameters, the parameters that you're kind of just saying, okay, let's try these things out. And then you can like move in and break down like what's exactly is happening in this model. So that class at the top right there, batch gradient descent. So that's just gonna like be the calculations of these derivatives, these gradients, and those are gonna be like the gradients of this loss function up here. And then the main meat of this is happening right here in the training. So you're breaking up into whatever like batch sizes you have, and then you're gonna send these inputs and labels, make a prediction, and then see how go to bed did, and then you're gonna update it. And so you're updating these weights right here, and then eventually you're gonna end up with something that hopefully is good. And so you can just see like implementation, loss function, and then just some things like help, so you can have these nice loss functions. But like batch vanilla gradient descent, your loss curve, that's going to be like nice and smooth. You know like exactly which step to take, which is going to be like the right direction. So loss is going to be nice and smooth, and it's going to bring you down to where you want to go. And your prediction is going to be nice and pretty. And then stochastic gradient descent. So this is just going to be basically like with batch size of 1. So you're basically kind of choosing random and then taking the direction that that data point is telling you to go in. And so the loss is going to be all crazy. That might actually be too crazy. But basically, it ends up actually like it worked again. Yeah, it worked. Yeah, and then you combine it, so it's like okay, take like that full. You know exactly where to go when you're doing the full data set. It's much less computationally expensive when you're just using one. So let's combine those ideas, create these like smaller batches, and then you end up with a loss function that's taking you very much in the right direction, but it's still much noisier. And then you also end up with a good prediction. And then this is like one of the simplest examples of machine learning, and it's once you get your head around this, everything becomes like much simpler going forward. And next week's presentation by Julius on neural networks will make much more sense. So yeah, if you have any questions, ask me, ask one of them.
How do we even begin to like split the learning rate that you selected, like
Yeah.
0.001? How do we even begin to decide what we want our learning rate to be?
Honestly, just start with like 0.01 right here, and then just go 0.001 and so forth and down. Yeah, you could probably come up with like different metrics, like if you want to like time how fast it's going to take you to get to like a good loss. Then you could see like the difference that has with the learning rate. This is like such a small example that it's not really going to play difference,
Right.
but
In practice, you should just use cross-validation, or if you want to like be really fancy, you can just add it to a level finder and do a hyper gradient, memory. So like you just treat it like a level finder with that, or do something like Bayesian black box optimization. So yeah, just kind of.
yeah, it's an art basically. There are so many methods that you can try out. Just play around, Google some things. There's another hand up. No? Yeah. That's it then.